Welcome to the Science and Engineering Practices, one of the three dimensions.
Good morning, everyone. Thank you for joining us today for this session. This is kind of part two, as we were just heard in the conversation yesterday that was about the cross-cutting concepts, but today we're going to be learning about science and engineering practices, which are one of those three dimensions for the Arizona Science Standards. My name is Sarah Sleesman. I am the Director of Science and STEM at the K-12 academic section of ADE. I'm really here to be your host today. I'm going to be alongside Sarah in the chat room and here to support anything she needs. Originally, my background, I came from Portland, Oregon, and moved out here and taught out here for 11 years in the Creighton School District, primarily in elementary. And for my experience with the department, this will be my third year there. And like I said, I'm just going to be your host to help Sarah in her facilitation. And I'm just going to tell you a little bit about Sarah because she has a plethora of wonderful things that she can really provide for us. So just to give her a little background, she's the executive director currently for the Arizona Science Teachers Association. She also works to support and consult educators. She also was an educator for 25 years. Whew, that's another thank you, thank you, thank you. She has also been a middle school administrator in New Mexico, as well as a director of curriculum in Missouri. She has an EDS from New Mexico State and administrative leadership, and has also completed coursework for a PhD in science education from the University of Missouri, Columbia. So, like I said, she has a lot of really great qualities and background experience to really make these, I feel like, opportunities meaningful and just keep it pretty simple. So like Bruce, what I just heard you sharing, you felt comfortable taking it back and pulling that out and starting to try. And that's the first step. And so in my role here, I'm just trying to create this rock star team to come in and help provide different experiences. So you hear a plethora of people because hearing a different voice is very helpful. So Sarah, with that, thank you for being here this morning. And I want to go ahead and turn it over to you.
Let me unmute myself, otherwise you'll never be able to hear me. Thank you, Sarah, and I am delighted to be here this morning. I know some of you had joined us yesterday, and maybe even joined, we did these sessions last week, so we are just really excited to be here. This focus, as Sarah said, is really to focus on that one of the three dimensions in our standards, which is really the science and engineering practices. And what is it? What does it, what are all these practices? Give you some feedback, background information, and then let's take a look and see what does it look like in our standards so you can have those conversations. To begin with our time together, I would really like us to take a moment, and I've got just a second, somebody in the waiting room, all right. I'd like for you to share with us who's in the room, and there's going to be a poll that will be coming up onto your screen. And if you don't mind, go ahead and complete. That's wonderful. A lot of educators, which is wonderful. Classroom teachers, about 78% of you are classroom teachers. So I'm going to just I'll share the poll so you can see who's in the room. By the end of today, that you'll feel confident enough to sit down, and as we're planning for next year, that you can sit down and have that conversation about the three dimensions and be able to really add to those conversations in your planning. We're going to utilize the chat, and as Sarah said earlier, this is the opportunity for you to increase your knowledge, and she's going to be watching the chat. So between the two of us, we'll be able to keep track of conversations and questions. My goal for our hour is to help you shift the way you think about teaching science. And to help achieve that goal, there are three objectives for our time together. By understanding how the Arizona Science Standards build students' knowledge and abilities over multiple years to make sense of the natural and design world, using science and engineering practices, students will be engaged in scientific inquiry and engineering design. As we go through our day, or I guess our morning time together, I'd like for you to take this information, reflect upon it, and implement it as well. And so just remember your AEIOUs. On April 23rd, this article was published in the Washington Post. Do you agree or disagree with this claim? Go ahead and use the chat room to share your thoughts. Brian disagrees. Lindsay kind of does both. We need to be flexible with the scientific method. That working alone won't do the work. Disagree, but it takes, Bridge is saying, to do reliable study. Bruce is saying it's a map for, the scientific method is a map for solving problems, but it needs to have other components added. Jamie, stating that the rigid linear format of the scientific method is not always being used. Yeah. Jerica, interesting, Jerica. It's saying that we need real science and not the basic form we used to introduce in students in school. Think about that. And I like Wilma's question, how is it being defined? And that could be a crucial piece, right? And Susan's saying that the second part of that statement, the idea of flexibility, is more accurate. Well, let's take a look at what all this article says here. The article states that the scientific method doesn't exist. And you'll have the link to this article as resources. It continues to state that science is about staying flexible, trying out a variety of tools as the questions we try to answer change before our eyes. It is a process, not a product. Think about that. It is a process, not a product. Thinking about that definition of science and your own experience of being in the science classroom, either as a teacher or as a student, how is this definition of science similar or different from what is in our science curriculum? So how is that definition similar or different than what is being in our what's in our science classroom that you may have experienced it either as a teacher or as a student? And you can add that to the chat. Bruce, is that similar to what we need to have kids problem solve? Different because it's becomes a process? Yeah. As your experience as a teacher or as a student, was it taught as a process or was it taught as a product? Was it flexible or not? Science has been very linear and is changing with added knowledge or better practices. Sometimes it's taught as a product. We've been trying to move towards problem solving, and that's why this new standards are so exciting. Jamie, the focus is on the final product, not the action students take to explore the concept. So let's take a look. I'm going to watch a short video titled Science in Action and how science works that might help us put a little light on this definition of where people are coming from about the scientific method. And then if you look at our standards and you do a word search, you're not really going to find the word scientific method in our standards. So what does all that mean and how we teach science? So let's take a look at watch this video, A Science in Action. Oops, sorry.
A couple years ago, a group of citizen scientists from the Western Cave Conservancy discovered a large, odd-looking spider in a cave in southern Oregon. They sent it to scientists in California. Recently, those scientists declared that spider a new species, Trogloraptor, and a member of a new family of spiders. Sounds straightforward, right?
Wrong.
Science definitely is not a linear step-by-step fashion. And science is unpredictable. It's dynamic. And I don't think it ever concludes. It just keeps going.
To communicate the real process of science, Judy and her colleagues developed this science flowchart to better explain how science works.
You may start in one area and you find the need to communicate with the community of scientists that you work with who might have additional or other ideas, and all of that helps to shape what science is and how we go about the process of science.
So let's take a look at the Trogloraptor discovery flowchart. It's less like a linear process and more like a pinball machine. Let's follow the path using the spider that the citizen scientists found as the pinball. They sent it to scientist Tracy Audizio, who is very curious about what lives in caves. She examined it for about 2 hours one night, trying to identify it by making observations and conferring with a colleague. They were stumped. The two researchers worked with the Academy's Charles Griswold and brought the specimen to him. He began his own observations.
I looked at it through the vial, not under a microscope, and I thought, oh, this is a brown recluse. It's about the same size, but when I looked at it closely, all the brown recluse characters, that is, various details of its anatomy, were wrong. The eyes were placed in the wrong arrangement. The jaws were wrong. The spinning organs were wrong. Everything about it was wrong.
Science often comes down to trial and error. The scientists shared ideas, and then...
Well, first we went to the books, and it didn't fit anything. After that, we carefully compared the new spider to descriptions of all spider families known in the world today, and we also consulted books on fossil spiders.
Along the way, the researchers made hypotheses about what this spider was and what it wasn't. Charles looked at the Academy's collections and others.
The more we looked at it, the more we realized that the details were wrong for every known family, living or extinct.
What do you do in science when you're stumped? Reach out to the scientific community.
You consult your colleagues who are knowledgeable, who know some things better than you do, and present the case for your conclusions, the evidence, and ask, what do you think of this? The word came back that, no, we've never seen this before.
They made a hypothesis.
We believe it's a new family related to the goblin spiders. But to suggest a new family is a very big deal. It doesn't happen very often, and the last time this happened in North America was more than 100 years ago.
Time for more input from the scientific community.
So we wrote the publication. They sent the paper and its conclusions to anonymous scientists, and they also agreed that we'd done a good job.
So let's celebrate. Wait, remember what Judy said?
And I don't think it ever concludes. It just keeps going, keeps going, keeps going.
And that's true with Trogloraptor.
In the arachnology lab at California Academy of Sciences, we're very interested in this major group of spiders. And we have a big team of scientists, students, postdoctoral researchers, who want to understand the evolution of goblin spiders.
So they're asking more questions, making more hypotheses and observations, doing more testing on Trogloraptor.
It has a surprising respiratory system, the way it breathes. The remarkable claws, which caused us to give it its name, are the subject of an anatomical study. Facundo Labarque actually dissected the feet of Trogloraptors and looked at the attachment of tendons. My PhD student is leading an effort to understand the phylogeny of the haplogyne spiders, especially the goblin spiders, through the use of molecular data.
And Trogloraptors in general? Those spiders live happily on in that cave, and probably other nearby caves.
The caves are protected.
So let's look at that process again, sped up this time. Pinball machine, right? And this process is true not just for scientists, but the rest of us too.
We all do science every day. You know, we all make observations, we ask questions, we communicate with people we know about our ideas, we come back to those original ideas. So I like to think that it demystifies science a bit. Everybody can do science.
Yeah, wondering if this is how science, I mean, if this is how science is done, logical but not linear, how do we teach science? Great question. We do encourage, we've encouraged that linear approach. I had ideas in the chat room. How would we teach science if this is how, if it's not done linear? I'll say it's logical. How do we teach it? So we think about this. This is a evidence-based, yeah. Going to the process, let them explore question. Having them to do the science, be collaborative. Jamie says it takes time, and I would agree with you completely, Jamie. How do we need to teach science to our students? Utilizing the practices where students are figuring out the world around them. This idea is not new of going to practices. It has emerged from the work of historians, philosophers, psychologists, and sociologists over the last 60 years. This perspective is an improvement over our previous approaches in several ways. Back in the early around 90s, that was when the science and the national science and education standards came out. It was really talking about this inquiry approach and to move us into inquiry, but there's this idea of this scientific method in here. Even though they weren't sure how to name it, it wasn't so much that we wanted to keep it as this controlled steps. And so unfortunately, the way it was implemented was that way. So this idea of having science and engineering practices, it minimizes the tendency to reduce scientific practice to a set of procedures, and I'm putting in quotes, the scientific method, such as identifying and controlling variables, classifying entities, and identifying source of error. This tendency overemphasizes experimental investigation at the expense of other practices, such as posing questions, arguing from evidence, modeling, critiquing, and communicating. Secondly, a focus on practices, the plural, avoids the mistaken impression that there is one distinctive approach common to all science, a single scientific method, or that uncertainty is a universal attribute of science. And thirdly, this attempts to develop the idea that science should be taught through a process of inquiry. inquiry, though, has been hampered by the lack of a common accepted definition over the years. So here are the 8 practices that are in our standards. And as you think back to that video, Science in Action, did you see or hear any of these practices? And when did you, if you did, can you just share with us when you did that, when you heard them, or when you saw them in action? And you can include that into the chat room. And if you look at these practices, look at the verbs. These practices are not the action of the teacher, but the actions of the students. Students should be actively engaged in the science practices and not just observe others doing science, teacher demonstrations, or memorizing content. These practices, and you saw those scientists actually doing those in a lot of those investigations in the video, the practices are what we want students to be doing. As students engage in these practices, they're going to gain greater proficiency in them. And by participating in the science and engineering practices, it will also enable students to develop a stronger understanding of the core ideas. If I'm, as a student, analyzing and interpreting the data, I'm going to be learning deeper about that core idea. If I am going to be engaging in argument from evidence, I'm going to be able to have to communicate my information that I know about those core ideas. But sometimes considering all 8 of those practices can be a bit overwhelming at first. And so we're going to think about these practices in 3 different groups. And as we observe the natural world, we're going to look at investigative practices. And then from that, we'll be getting some data, and then we'll be able to utilize some sense-making practices. And finally, we'll be able to utilize critiquing practices. Science is fundamentally about students making sense of the natural world around them. In order to do this, scientists engage in a number of investigating practices: asking questions and defining problems, planning and carrying out investigations to gather data about the world. Once scientists have engaged in these investigative practices, they have data that they engage in, the sense-making practices. And through the sense-making practices, students analyze the data looking for patterns, construct explanations, and develop models to better understand how or why different natural phenomena occur. And finally, these processes can often result in competing ideas, such as multiple alternative explanations. Consequently, scientists often engage in critiquing practices, where they engage in argument from evidence and evaluate multiple possibilities. We will be dividing into all 8 science practices, but the 3 groups are one entry point to help us think about the practices. Do you have any questions about the grouping of these practices at this point in time? Well, let's dig a little bit deeper into these practices, and let's begin with the investigative practices and the investigative practice of asking questions and defining problems. Asking questions is a fundamental way to gather relevant information in the process of making sense of phenomena. Students should develop questions that can be answered using empirical evidence. And in engineering, The process of gathering information begins with defining a problem. Questions are asked by students to help gather information that can be used to make sense of a problem. Another investigative practice is planning and carrying out investigations. This practice may seem familiar to you. It might remind you of our initial discussion this morning, the scientific method. This practice is a systematic way, a logical way to gather data about the natural world, either in the field or in the laboratory setting. When students engage in this science practice, they design investigations that will produce data that can be used to answer scientific questions. This process includes determining the goal of the investigation, developing predictions, and designing procedures, such as identifying experimental variables and controls. Planning an investigation requires significantly more knowledge and skills than carrying out the investigation. There is a lot of existing curriculum which has students conduct experiments, but few of them have the students design the experiments. Thus, it is important to modify curriculum to better align with this science practice. Using mathematics and computational thinking is the third investigative practice. Mathematical and computational approaches enable scientists and engineers to predict the behavior of systems and test the validity of such predictions. This practice is all about finding precise ways to describe the patterns and processes that make up scientific and engineered systems. The practice of using mathematics and computational thinking is about learning how to both apply formula and tools that already exist and create new ones. These are some ways that students might engage in using mathematical and computational thinking. Students may be measuring using traditional or non-traditional units. They're graphing, they're creating a mathematical model, they're using and creating a scale, they're using equations to make predictions, they're comparing quantities, and they're solving equations such as physics equations. These three practices are the investigative practices that help students ask questions and conduct investigations about the natural world, which result in the production of data. In the chat room, I'd like for you to share how these three practices compare or contrast to the Arizona 2004 standards. How do these three compare or contrast to our old standards? Go ahead and put your ideas in the chat room. Yeah, Lindsay seemed. Not as the practices, did we, Lindsay? Yeah, I would agree with that. Mira, I'm assuming you're thinking that one of the contrasts is that this is going to require more students' critical thinking. Yeah, the students ask the questions. I think throughout our pedagogical training as to become a teacher, there's a lot of things about what kind of questions are the teachers asking the students, right? And that may even be part of your evaluation. What kind of questions are you asking? Lower end questions? Are you asking higher end? But what we really need to be thinking about in science, yes, we are going to, as the facilitators, ask questions, but our students need to be asking questions about the natural world, about the phenomena, about the data. And the questions we're going to ask them are going to be more questions about, so share with me what the data is sharing, how you analyze that data. Can you tell me more about the patterns that you are seeing? So we're going to be asking the questions and helping the students think about the patterns, the cross-cutting concepts, the scientific engineering practices that they're using. But our students will be asking questions about the content, the core ideas, the natural world that they're observing, the phenomena. And so thinking about this, how do these relate to the scientific method? How do these three practices relate to the scientific method? And some of you have kind of already answered that. The method was the way to teach because the experiment had one outcome. Yeah. It was already designed for the students. That method of that experiment that the students were doing was validating what students have already read or done. It's more student directed, student led. Still investigating. Well, one of the first, let's go to sense-making practices. So we've got our data from investigating and asking questions and defining the problems, and we've used our mathematics to create some charts. So one of our first sense-making practices is then analyzing and interpreting data. These investigations provide data that, when analyzed, provides greater insight into cause and effect relationships. If you remember, if you were with me yesterday or last week, the cross-cutting concepts, cause and effect is that cross-cutting concept. So when we analyze and interpret the data, it provides greater insight into that cross-cutting concept of cause and effect relationships. Often, until analyzed, data has little meaning. Students may use a number of tools and techniques to make sense of the data. Just like in using mathematics and computational thinking, students will use data, they'll use tables, they'll use graphs or other representations, and they will use math as a tool to do science. The second sense-making practice is developing and using models. Models are defined by how they are used. Scientific models are sense-making tools that help us predict and explain the world. In engineering, models are used for analyzing, testing, and designing. Models are distinct from the representational forms they take. They can take the form of diagrams, they can take the form of words, they can take the form of equations or computer programs, as long as they embody ideas about how and why the phenomena occurs, or about the components and relationships of the system being studied. A model explains and or predicts the phenomenon, and students should be able to evaluate a model. Models can range from simple to more complex, and they may require little material or to specialized material and or technology. So as we think about this, a simple drawing of a heart is not a good example of a model in science. If, however, students create or use a heart model in which they can manipulate the opening and closing of a valve in order to predict what happens when a valve does not close properly, that would be a model as it relates to the scientific practice of modeling. As the professional, you will need to consider these questions as you utilize models in your classroom. And there are 4 questions that you need to be thinking about. Do students create or use the model to explain natural phenomena? Do students create or use the model to describe natural phenomena? Do students create or use the model to predict natural phenomena? Can students evaluate the model for merits and or limitations? If students can do that and they're using the models for that, then you are having the students develop and using models as what is in this practice. So the key thing there is students need to be using it to describe, they need to be using it to explain, they need to be able to predict phenomena, and they should be able to evaluate the model on its merits and or limitations. The third practice that is part of the sense making, if I'm trying to make sense of the world, sense of the phenomena, is constructing explanations and designing solutions. Constructing explanations pertains to science, while designing solutions pertains to engineering. Science explanations are accounts that link scientific theory with specific observations or phenomena. For example, they explain an observed relationship between variables and describe the mechanism that support cause and effect inferences about them. They address a question about a specific phenomenon. They are not abstract descriptions or definitions of a science concept. Explanations include a how or why account of the phenomenon that draws on a scientific model or generalized principles that use core ideas. Explanations are based on evidence. An exclamation includes a claim that relates how a variable or variables relate to another variable or set of variables. A claim is often made in response to a question, and in the process of answering the question, scientists often design investigations to generate the data. So a scientific explanation has 3 components: a claim, a clear answer to a question about how or why a phenomenon occurs. 2, evidence, the data, the measurements or observations that support the claim being made. And the third component is reasoning, an explanation of why the evidence supports the claim, which often includes scientific principles. You may have heard of this claim, evidence, reasoning as a CER. So, the sense-making practices. These science practices include the many ways that data can be analyzed and made sense of by students as they develop models and explanations about the natural world. I want you to think, why do you think these 3 are in the sense-making category rather than the investigative or critiquing category? Go ahead and add your ideas to the chat room. Why would these 3 practices be utilized in a sense-making category rather than the investigative or the critiquing? Yes, Bridget, I can repeat the CER. Claim, evidence, and reasoning. And it relates back to those explanations. When the students are either orally or verbally describing the phenomena, they're going to be talking about the how or the why of what it has. And so they'll make a claim, they'll use evidence from their data and make reasoning, tying it back to the core idea, the science. Lindsay's saying that these practices really help us make sense of the data that was collected. Yeah, we can collect all the data, but we need to make sense of it. We need our students to make sense of it for themselves, not the teacher having to explain it. I know sometimes when I was in the classroom, that sometimes my time was limited, so I did all the analysis of the data. Well, I was making sense of the data. I was making sense of what was happening, but my students weren't. Yeah, when you're trying to understand something, the models that we construct help us. So you think about last question, which one of these do you think will be most challenging for students? And which one of these sense-making practices will be challenging for the teachers to facilitate? And so when you answer the question in the chat room, put down S for students, this is what's going to be the most challenging, and T for teachers. So I know you don't have to type up the whole word. Which one do you think is going to be most challenging for students, and which one's going to be the most challenging for teachers? Constructing the explanations, the how or the why is going to be challenging for students. Yeah. Developing and using models for both, yes. These are new. It's going to be new for them, new for us. Yeah, designing solutions and they all take time. Let's take a look at our last area of practices. Argumentation is a process for reaching agreements about explanations and design solutions. In science, reasoning and argument based on evidence are essential in identifying the best explanation for a natural phenomenon. Student engagement in scientific argumentation is critical if students are to understand the culture in which scientists live and how to apply science and engineering for the benefit of society. As such, argument is a process based on evidence and reasoning that leads to explanations acceptable by the scientific community and design solutions acceptable by the engineering community. Argument in science goes beyond reaching agreements in explanations and designing solutions. Whether investigating a phenomenon, testing a design, or constructing a model to provide a mechanism for an explanation, students are expected to use argumentation to listen to, compare, and evaluate competing ideas and methods based on their merits. Scientists and engineers engage in argumentation when investigating a phenomenon, testing a design solution, resolving questions about measurement, building data models, and using evidence to evaluate claims. So how is argumentation similar or different from explanations? Engaging in argument from evidence has three main points. First, students listen to, compare, and evaluate competing ideas or solutions. Secondly, they identify the best explanation or solution. And third is evidence-based. Whereas constructing explanations develop one or more explanations of a phenomena or solutions to a problem, and two is evidence-based. The key point about differences between argumentations and explanations is that arguments feature competing claims. Argumentation includes the process of selecting the best claim. The second critiquing practice is obtaining, evaluating, and communicating information. Being a critical consumer of information about science and engineering requires the ability to read or view reports of scientific or technological advances or applications and to recognize the salient ideas, identify sources of error and methodological flaws, distinguish observations from inferences, arguments from explanations, and claims from evidence. Communicating information, ideas, and evidence can be done in multiple ways. Students can use tables, they can use diagrams, they can use graphs, as well as orally, in writing, and through extended discussions. Students read and evaluate text to obtain scientific information. Students compare and combine information from multiple texts, considering the strengths of the information and sources. The critiquing practices. These science practices, which are often left out of K-12 science education, emphasize students evaluating and arguing about different models and explanations, which ultimately helps them develop stronger understandings about the natural world. Why do you think these practices are often left out of the curriculum? And you can answer these questions in the chat room. And if the critiquing practices are more emphasized in the curriculum, how might students' understanding of the core ideas be impacted? Time. I would agree with both Bridget and Tammy. This takes time. And I think you're right. That's probably why they're left out. But if we start utilizing this, how is that going to impact the students' understanding of the core ideas? Maybe lack of resources. The lack of not having high quality nonfiction resources. Where to go to find those resources. Science is fundamentally about making sense of the natural world. In order to do this, scientists engage in a number of investigative practices in that they ask questions and carry out investigations to gather data about the world. Once scientists have data, they engage in sense-making practices in that they analyze the data looking for patterns, construct explanations, and develop models to better understand how or why different phenomena occur. Finally, these processes can often result in competing ideas, such as multiple alternative explanations. Consequently, scientists often engage in critiquing practices where they engage in argument from evidence and evaluate multiple possibilities. And because these practices can enter into the process as we learn about our natural world, we do not see them as linear steps. Instead, we can see them more like this, where they are like that ping pong ball in that video we watched earlier. As students are figuring out the phenomenon, they will go from one practice to another. Are these practices logical? Yes. Are they linear? No. If you have questions, go ahead and please type them in the chat room, but I'm going to continue on because I am also cognizant of our time together. So we're going to take a look at the Arizona standards and this dimension of the science and engineering practices. And so here is a page from the first grade standards. And on the right-hand side of the column is our standards. And you might see the practices right there. The science and engineering practices in blue. In this standard, there actually are two science and engineering practices. Obtain, evaluate, and communicate information, and evidence-based explanation. All grade levels, K through 12, are similar to this format. The science and engineering practice is part of the actual standard. Although all 8 SEPs, or science and engineering practices, are in all grades K through 12, the expectation for what students should know and be able to do with each of these practices are different for each education level. So let's take a look at these progressions. On the ADE website, where you can download the standards, is a link to the vertical progressions on the right-hand side. When you open that menu, there is a progression, the knowing ideas of science, cross-cutting concepts, and the scientific engineering practices, which looks like this. Each practice has its own page listed with the expectations of what students should know and be able to do for that SEP. We call these little bullets elements. So let's take a look. This one happens to be on asking questions and defining problems, but let's take a look at planning and carrying out investigations more closely. Look at the bullets. Look at what kids are supposed to be doing at each grade level. What do you notice? Does this progression for K-12, carrying out investigations, make sense? Are there any wonderings or surprises as you look at specifically this practice of planning and carrying out investigations? You can add your thoughts to the chat room. What are your notices? What are your wonderings? Does this progression make sense as we go from K2 to 3-5 to 6-8 to 9-12? Each science and engineering practice has a progression that is similar to this one to help you as the professional to scaffold students' understanding of the SEP while making sense of the phenomenon. You know where you need to start, and it does scaffold. So you think about your own grade level standards. Which practices do you explicitly teach now? And which practices do you feel your students will have the most experience with in the fall? Just something for you to reflect upon. Which ones do you currently explicitly teach now? And which ones do you think your students will already have experience with that maybe you may not have to scaffold as much? In the beginning of our session today, I shared this article. I would agree that there's no such thing as a scientific method, no single set of steps or one-size-fits-all solution to the problems we face. Ask any scientist what they do, individually or collectively. What they do is too diverse, too dynamic, too difficult to follow one recipe. And that our new standards and the dimensions of the SEPs will engage students in obtaining and using information obtained from investigations and other sources, developing and using models, constructing explanations, and communicating arguments that support these explanations. Some key takeaways that I would like for you to remember. Our students need to inquire like a scientist, think like a scientist, quantify like a scientist, read like a scientist, talk like a scientist, write like a scientist, critique like a scientist, argue like a scientist. How do we do that? With phenomenon-based instruction where students are figuring out the phenomena like a scientist or an engineer. What questions do you have? Well, I know our time is about up, and I just want to let you know that the Arizona Science Teachers Association has workshops and webinars. They'll be coming out throughout the summer on each individual practice. We do quite, we're taking the ones that we do face-to-face to the online platform, so you'll be seeing those coming out. That's at AZSTA, and you can sign up for those. But it's on the individual practices, because there's so much, as you looked at that progression, there's so much to learn in as the facilitator of helping your students figure out the phenomenon, that we want to give you those supports to do that. Thank you so very much for joining me today. And I'll let Sarah take over and talk about the evaluation.
Perfect. Thank you so much, Sarah. That was amazing. You so eloquently went through understanding a lot more about those science and engineering practices today with us. And you really just how kids make sense of phenomena by doing the science, like they are that scientist, like they are that engineer. So I just want to thank you again for helping to support through the state of Arizona, our science community across the state. So we appreciate your time and being here and taking the time to also put all of that together. I do want to go through a couple logisticals for the end of this. We also have, like ASTA has a lot of really good professional learning coming up. At ADE, I have kind of what I call my rock star team right now, where I have different people across the state to come in and do some different learning experiences. So Bruce, like I told you, we also have one on the 5E model and how to incorporate that into three-dimensional learning by Rebecca Grelli, our science specialist at the department, and she has a couple others she does. But just so you know, manually, I will put in the attendance in the next 24 to 48 business hours. So it might take me till Monday by the end of the day. But once that is done, what you will receive is an email from the EMS system where you'll take a survey, and then you can obtain your certificate. I will not email you a certificate. It does not come directly from me. It all comes through that management system through the EMS. So you go in and it says that you've missed the course. You have not missed the course. You just haven't been marked yet as completed. So I have to go and do name by name matches and put those in. So following that, I will also send you an email for the links and the resources that Sarah has put together. So she has put together a PDF with all of her resources, or all of the presentation in there, as well as a list of resources for you that she's created. So you will also get that. So with that in mind, I think we've reached the end of our time today. So thank you for coming here, and thank you for joining us. And again, Sarah, thank you so much. That was wonderful.
Thank you, Sarah. Thank you, everyone. Stay safe and healthy, and looking forward to seeing you at another professional learning opportunity that we have here in Arizona.